I hope physics is being successful in attracting you with the force of love for knowledge and you are just orbiting some topics of physics. So today we are going to talk about equipotential surface and about last class. Means today we are going to compare the gravitational potential with the electrostatic potential. So if you are doing B.Sc, then you know about electrostatic potential. But if you are in 12th class, let me revise you this topic once again so that it will be easier for you. So basically, the potential due to a charge, due to a static charge, is known as electrostatic potential. What does this mean? Actually, potential energy is the energy stored while bringing a charge from a point at infinity to a particular position around a point charge. But the energy per unit mass means something like density. You can say mass is, you can compare mass with the potential energy and density with the potential energy per unit mass, right? So I guess this thing is clear. So we are going to talk about the potential per unit mass, which is known as the potential of that point due to a point charge, right? So suppose we are bringing a charge from a distance of infinity to a particular position at some distance from the point charge, just like we did it in the last class for a point mass. So suppose this is a point charge Q. We know that there are two types of charges, positive and negative, in nature. So suppose this charge is Q. We do this for positive charge, and if there is a negative charge in this case, it will have a negative sign. We know that the potential due to gravitation had only one sign, but here as we have two types of charges, so we will have two formula, means basically one formula, but it will change with the sign of the charge, means the nature of the charge. So here is the point charge Q. Suppose we are bringing a point, very small charge, that is test charge dq, from a point at infinity to a point at a distance r from the point charge q. So we are going to calculate potential due to this point charge q at a distance r from this. So we will bring a test charge q and calculate the work done. So what is the formula of work done? Work done is F dx, right? Let us suppose here we have two charges. We know the formula of electrostatic force. What is the formula of electrostatic force? We know that it is 1 by 4 pi epsilon naught q1 q2 by r square with multiplied with some permittivity. If there is some other medium except air and vacuum. For air there is some permittivity, but for vacuum it is 1. So in this case we are calculating this for vacuum. We know that the gravitational constant is universal, that's why it is just a simple g. But for charges there is a permittivity, that's why the constant is variable, means it varies with medium. So actually here the force will be, we can say that, suppose q by r square, means suppose here it is at a distance, we are talking about a random point, it is at a distance x. We are bringing it from infinite, we are talking about a point x at a distance, so it will be q1 q2 by r square into some constant. Let us suppose it is k. Okay, and if there is some permittivity, we will say that there will be the permittivity will be divided, right? So now we are going to integrate this force multiplied with some displacement dx. Suppose from this point we are displacing it to a distance of dx. Here the force is acting, let us suppose this is positive, this is positive. As you can see, there is no negative sign in front of the both of the charges, so we will consider that both of the charges are positive. So like charges repel, that's why the force will act along this direction, but we are displacing the particle in this direction. So means we can say that the angle between the force and the displacement will be 180 degree. So here we are going to take dot product. We know that the dot product of force with displacement is work done. So as dot product will dot product means these two things multiplied with cos of the angle between them. So cos 180 is -1. So we will get a -1 sign in front of it multiplied with dx, right? Yes. Now we are going to integrate it. I am going to integrate it from infinity to the point r. It is at a distance of infinity from the q initially, and we will take it to a distance of r from q. So let us integrate this. After integrating this, we will get kq dq by integrating x square means x to the power -2 plus 1 equals to x to the power -1 divided by -1 means we will get x with a minus sign, and here is a -1, and actually we are changing the x from infinity to r. Okay, I guess you are able to understand what I have done here, the integration, right? So now finally we will get 1 by infinity will be equals to 0. So now by putting r we will be able to get the potential, the work done to bring the charge dq from infinity to the position of distance r from the point charge q will be equals to kq dq by r, as the negative sign will cancel out and give us a positive result. So now we want to actually calculate the work done per unit charge. As we are doing this thing in gravitational potential, we are dividing the mass, as here the charge is the cause of the attraction or repulsion, so we are here dividing the charge. So now we will get the potential as kq by r dividing the charge dq. Okay, this is the formula we have now. So now we have the potential due to this point charge q at a distance of r from it. So now we are going to calculate potential. Sorry, this is potential, right? Yes, we have now potential. We are going to calculate potential due to the spherical shell. We can do the same type of integration and all to calculate the potential due to a spherical shell. We have to take a sphere along a radius AB. A point P lies outside the shell. We are going to take an elemental ring by making it sliced through due to CDEF planes, and here from the center it will make an angle of theta, and as this is really very small, this will make an angle d theta really very small, and hence this arc will be equal to r d theta. This length will be equal to this radius into 2 pi, means 2 pi r is perimeter will be, so multiplying this length, this arc with its perimeter will give us the surface area. So its surface area will be r sine theta, its radius, into 2 pi. means we will get 2 pi r square sine theta d theta, right? From this we can see that if I draw the distance of a ring from the point P, let us say it to be x. For each ring the x will vary. For the initial ring taken from here, a very small ring, it will be equals to, suppose this is r, from center it is at a distance r, then this small for the small ring the distance will be equal to small r minus capital R, that is the radius of the sphere. And for the last sphere, that is at the last end of the sphere, means again a very small ring, it will be equals to capital R plus small r. So from this we can see that here we have a we have polygon, right? So from this we can do vector addition and see that x vector will be equals to small r vector minus capital R vector. So we will get x square plus equals to r square plus capital R square minus 2r cos theta, because the angle between capital R and small r is here theta, because this is the radius of the sphere and is equals to r. So now we can get that dx will be equals to, differentiating both sides, these are constants, so it will be equal to 0, and this will be equals to my 2r sin theta. So we will get x equals to 2r sin theta d theta by dx, right? So now we have to put this, use this equation to calculate potential due to the complete sphere. Let us first calculate the potential due to this elemental ring. So for this elemental ring the potential will be k q. For q we have to consider the surface density, surface charge density means the charge per unit surface area, sigma, which will be equals to q, the total charge, divided by its surface area, means 4 by 3, sorry, this is actually the volume, 4 pi r square, right? Charge divided by the surface area is sigma, sigma multiplied with the volume, surface area of this ring will give the charge on this ring. So we are going to multiply q by 4 pi r square with, where is the surface area, where is this, here, 2 pi r square. Let me clean this part a little bit so that I can write. So v is equals to kq by r, right? Here k will be given for a particular medium and q will be equals to sigma into, sigma means surface charge density multiplied with the surface area of this ring, means we will get the amount of charge present on this elemental ring. So this will be equals to q by 4 pi r square, which is sigma, multiplied with the surface area 2 pi r square sin theta d theta. We know that x square equals to r square plus capital R square minus 2r sin theta, right? And differentiating it will give 2x dx equals to 2r, sorry, here cos theta, and here differentiating it we will get sin theta. And from this we can say that x equals to 2 will cancel out, x equals to smaller capital R sin theta divided by dx, right? From obviously vector addition, law of vector addition, so this will be equals to k cube by 4 pi r square. Oh sorry, here I have not divided the r. What is actually r? R is the distance from the point charge to the point at which we want to calculate potential. Here the charge is on the ring and ring is at a distance of x from the point P at which we want to calculate potential. So this whole thing will be divided by x, and here we will put let me first cancel this something, 4 pi r square, we will get 2 k cube by 2 multiplied with sine theta d theta by x. Here I can replace x with capital R small r sine theta d theta. Sine theta d theta will cancel out. Now I have k cube by 2, and yes, divided by dx means dx will get multiplied into dx, and taking this constant. We have to integrate this to calculate the potential due to the complete sphere. So we will integrate it for a ring at this position, a very small ring, and to a ring at this B position. So for this position A very small ring will be there, and distance of the ring from the point P, it will be capital R minus small r, right? So let us put the limits. We are integrating this from capital R small r minus capital R to small r plus capital R. So we will get, if integrating dx will give us x, so integrating x from r plus r to r minus r, we will get k cube by 2 small r capital R into 2 capital R. So 2 capital R will cancel out, and finally we will get the potential due to this sphere with some charge distributed on its surface evenly, right? The charge will spread evenly, so the potential due to this sphere at point P will be equals to k q by r. Charge on the sphere a constant, and the distance from the center, right? Here you can see that it feels like the sphere is actually a point charge. Whole charge of the sphere is concentrated at the point O, the center of the sphere. It feels something like that because the distance from the center is smaller. Here we have put it smaller, and this is the thing. And for a point on the surface, we will change the limits. It will be equal to, for a point on surface, initial point will have 0 distance, and the final ring will have distance of 2r. You can integrate it and calculate the same, and you can also just replace small r with capital R and get the value of v equals to k cube by capital R, means potential due to the sphere on the surface for a point inside the surface. Let us suppose this is the sphere. We are considering a point on the surface. Here is the center, here the distance small r, here the distance capital R. For this initial ring, the distance will be capital R minus small r, and for this ring it will be equals to capital R plus small r. So we will integrate from capital R minus small r to capital R plus small r, and if you will put the limits here, you will get the answer to be potential due to sphere inside the sphere will be equals to k cube by capital R. That is the potential on the surface. You will see that potential on the surface and potential inside the sphere is equal, but we will see the same difference, that is the same discontinuity in field, as there was a discontinuity in gravitational field due to sphere. At the point of the surface, you will see the same discontinuity. Discontinuity means on the surface the potential will be equal to kq by r square, but inside the sphere it will be equals to 0. So first let me erase it. That potential is kq by r. Field is the negative gradient of potential. So we can use this formula and calculate the electrostatic potential due to a charge at a point inside the sphere, spherical shell, outside the shell, and on the surface. So for outside point, we will simply differentiate it and get the value of kq by r square. For the point on the surface, you can replace small r with the capital R and get a formula of something looking like this. And for a point inside, it will be equals to 0, because for a point inside, potential is kq by capital R, where everything is constant, and will be equals to 0. Differentiation of constants is equals to 0. Actually here something named Gauss law is applied, and Gauss law is actually a formula which is a something like changing one type of integral to another form. Simply you know that Gauss law for electrostatic is E dot ds, integral E dot ds equals to q by epsilon naught, right? So here from this thing you can actually know that this is the flux due to the charge and this is the charge. Means for a Gaussian surface, if there is no charge inside, the electric field will be equal to 0. And let us suppose this here is a spherical shell, considering this point, and make a Gaussian surface with this point, then you will see that there is no charge inside, the charge is outside. So as there is no charge inside the Gaussian surface, so we will say that there is no field, as if this thing is equals to 0, this thing will obviously be equals to 0, and if this thing is equals to 0, as the surface cannot be equals to 0, it means the field is equals to 0, right? So here as there is no charge inside the sphere, and therefore for a point inside the sphere, if we make a Gaussian surface, the charge will the field will be equals to 0. I hope this thing is clear. Electrostatic is actually a beautiful topic and a little bit difficult for thing to explain initially, but is a really very beautiful thing to understand. So now I have potential and field due to electric charge and m mass. Means I actually have gravitational potential, electrostatic potential due to a mass, due to a spherical shell, and gravitational field and electrostatic field due to a spherical shell. I will just write it down and will show you some graph. Means how the potential and field varies at different points. So here for gravitational and electrostatic field and potential, I will make a table, something like table, and show you how the graph will look like inside, outside, and on the surface of the sphere, right? So for an inside point, went potential, field. So potential inside is as electrostatic is kq by capital R, outside kq by small r, on the surface kq by capital R. Actually gravitational force is weaker than electrostatic force, and nuclear force is stronger than electrostatic. Means nuclear force is stronger than both of the force, and gravitational force is weaker than electrostatic force. But still it is a dominant force, because maybe this chalk is neutral in charge, because same amount of positive charge and same amount of negative charge lie on it, but it has a mass, right? That's why some gravitational force will act on it. But our body actually, there we know about signals, Neuron signals and electrolytes in our body help to conduct everything on our body. So inside our body actually charges are working. So electrostatic force is essential, gravitational force, every type of force is essential, nuclear force is essential, as every atom is important. You know about atomic. Oh sorry, let's jump to the topic. Actually I am talking unnecessary topics. So here potential field will inside will be equal to 0, outside will be equal to k cube by r square, and on the surface k cube by capital R square. Gravitational potential G minus G m by inside, yes, small r, outside by capital R, minus G m by small r minus G m by capital R. Inside field equals to 0 and outside field equals to minus G m by r square, and for a point on the surface it is equal to minus G m by capital R square. So one thing here you can see is field is most negative, means has a large magnitude and a negative value on the surface, and is 0 inside the spherical shell, and also electrostatic has the highest magnitude on the surface, right? Let us do 4 graphs for this, means 4 graphs for each of the column. Here actually we draw spheres just to represent that at which point how much amount of field or potential is there, so that it will be easier to visualize. So I am starting with electrostatic one. Sorry, I have drawn this a little bit lower. So let's start with gravitational one, and obviously we had started with gravitational, so let us start with this. So here first potential is minus Gm by r outside the sphere, and inside and on the surface it is minus Gm by capital R, and small r is actually greater than capital R, because for a point outside the sphere the distance will be greater than the radius, right? So it means that for on the surface and inside the shell the potential is most negative and is equal to minus Gm by r. So for this range it will be equal to minus Gm by r. Here it is the radius, right? And it will decrease as the distance increases, and if the distance is near infinity it will tend to 0, means it will look something like this, right? And for field it will be 0 for a point inside, but suddenly it will have the magnitude of minus Gm by small r square. Small r square means, yes, let us suppose this is minus Gm by capital R square. Sorry, inside it is 0, and for the point on the surface it is equal to minus Gm by capital R square, means for 2 point it is only minus Gm by capital R square. It looks something like this. So after means outside the shell it will be equal to minus Gm by small r square, as small r is greater than capital R, means the potential means the field will decrease in magnitude but has a negative value, and when the distance will tend to infinity, the field will tend to 0. So here actually you can see one thing, that the decrease will be more, because here it is r square and here it, for potential it is just r, and as this is square, it is square of r, so it will increase, it decrease more rapidly, decrease in magnitude but increase in value more rapidly, right? Here it is infinity and will tend to 0. Now we will draw for electrostatic potential. Similar manner, just flip the thing, means just flip the graph, take the mirror image of this graph along the x-axis, means using the x-axis as mirror, take the mirror image of the graph, right? So now let's draw for electrostatic potential. So it has the maximum value of kq by capital R on the surface and inside the sphere, and the potential decreases with distance and tends to 0 as distance tends to infinity, and its field is inside 0 but has a value of kq by r square, capital R square, on the surface, and this field also decreases with distance but more rapidly outside the sphere. I guess everything is clear. Let me tell you one thing, equipotential surface. What is equipotential surface? The thing lies in inside the name. Equi means same, potential means obviously potential. So equipotential means a surface where every point has same potential. What is potential? We are calculating potential due to a charge, means the work done per unit charge or mass to displace it from infinity to that particular point, right? So equipotential means the surface where potential is same. Suppose we know that here the value of potential is kq by r on the surface, right? Means for the sphere, for the whole sphere on the surface, there will be kq by r potential, right? Means every point on the surface have kq by r potential, means it is a equipotential surface. So actually the field is perpendicular to the surface for a equipotential surface. I can show you one thing. Suppose this is a equipotential surface and here the field is perpendicular to it, and therefore as the field is perpendicular to the equipotential surface, work done is required to displace it on the surface. Means if you want to displace a charge present on surface to another point on the surface, means suppose it is north pole and it is south pole of the surface, you want to displace a charge from south pole to north pole, then the work done will be equals to 0 to do this work, because electrostatic work done, because there is no change in potential, and as the potential is equal, no work is done. So here the field is perpendicular to it, that's why there is 0 work done, and you can prove both the things by taking by just assuming that the other thing is true. Means if you assume that the potential the field is perpendicular to the surface, you can prove that the work done will be 0 to displace it on the surface, and if you assume that the work done is 0 to displace it on the surface, you can show that the field is always perpendicular to the surface, the equipotential surface. So this is for today. In the next class, we will talk about solid sphere. Thank you.